The next part of reaction mechanism that we're going to talk about is how it relates to the rate law. For those who are not paying attention, we are moving on to 5.8 now. So, another information given by a reaction mechanism is its molecularity, which is defined as the number of species that must collide to produce the reaction indicated by that step. So if a reaction involves one molecule, it is called unimolecular. If it includes 2 or 3 species, then it's bimolecular for 2 or termomolecular for 3. And so then I have this graph, or this chart table underneath on the next slide, that shows all of the possibilities that could be for the unimolecular, bimolecular, and termomolecular options. So when it's unimolecular, this would be like the decomposition part for unimolecular. Bimolecular, you could either have 2 of the same reactant, or you could have 2 different reactants reacting. And then termomolecular, you could have multiples of the same reactant, or you could have different reactants. Now, again, this is predicting. This might not necessarily be true, because before we talked about how the rate law should match the rate determining step. And remember that in order to determine what order everything is, it's by experimental data. But if you don't have an experimental data and all you have is the reaction mechanism, then you can make some inferences to try and make the orders match. So, like for example, for the bimolecular, when it's 2 of the same thing, you have to make it different somehow. So then, like unimolecular, so they said that it was to second order because it was 2 of them reacting, okay? Or for like the termomolecular, when they have 2 A's plus a B, they put the A in second order and B in first order for their rate law. Is that really how it is? We don't know if we don't have any experimental data. But this would just be predicting what it could be from just the reactions that you're given. Okay? So for reaction mechanisms in which the elementary step is irreversible, or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step, aka the rate determining step. So again, the rate law should match that rate determining step, or it matches the molecularity of that rate determining step. So if there are 2 molecules in play, it's bimolecular, so the rate law should show you that it's bimolecular. Example 12. The rate law for the reaction represented above is rate is equal to the constant times the concentration of NO2 times the concentration of F2. Which of the choices could be the first elementary step of a 2-step mechanism for the reaction if the first step is slow and the second step is fast?
Isn't it B?
Yes, it is. Why?
Because the F2 and the F cancel, but only one of the F2's cancel.
The F and the F2 cancel. Yes. So, the way that I thought about it was that, like, if this is the first step and it's the rate determining step, and the reaction rate law has to match the rate determining step, I was looking for reactants that matched those. So my possibility of choices could either be B or D, because the other 2, A and C, do not have the correct substances in the rate law. So that's how I thought about it. Can you say that again, what you thought, Kaylin?
I guess I wasn't really going off the rate law, I was just going off the equation.
Oh, off the equation.
Then why is it B instead of C?
It's not C because there's an F2 in the rate law.
Oh, it's an F2.
And yes, and it's only an F in C. So that would be maybe that would be like the second. Maybe that would be the second step where you cancel off the F, and you double your NO2s and you double your NO2Fs, but that would not be able to be the first step. So that's another way to look at some of your data for weight loss. Do you have a question, Jude?